65 million years ago, the dinosaurs dominated Earth, and then over a very short time, geologically speaking, not just the dinosaurs became extinct, but 3 out of every 4 living species. An amazing catastrophe. Most scientists now accept that the reason for that was because Earth was impacted with an asteroid about the size of Greater Moncton. Not bigger than that, or maybe a little bigger than that. So the question is, what can we do and what should we do about this? But although the impact hypothesis had been proposed as long ago as 1980, for the first decade and a bit after that, there were many skeptics. They said, show us the proof. In particular, show us the crater. Now, it isn't that there wasn't any proof. For example, if you look in the geological layers that corresponded to that time, they were particularly rich in the element iridium. Iridium is very rare on the surface of Earth, but is more common in meteorites and asteroids. Also, it isn't that there weren't any impact craters that had been recognized. There were many, in fact, right here in Canada. In northern Quebec, Clearwater Lakes actually is a dual impact signature, and one of the biggest and oldest impact craters, Lac Manicouagan, and there's actually an impact crater on the continental shelf south of Nova Scotia. But none of the impact craters were the right age and the right size to correspond to the extinction event. That's where our story takes us to Fredericton, or more exactly, to someone who grew up in Fredericton, Alan Hildebrand, shown here. Alan studied geology, but he always had a passion for astronomy, and he got interested in this question of where was the impact crater that corresponded to the extinction of species. And through geologic evidence, he had a pretty good hunch that it was somewhere at least near the Caribbean, but no one could find the exact crater until Alan. He found that it was in the Yucatan Peninsula of Mexico. I show it here. Do you see the crater? I don't see the crater. Maybe this will help. This actually shows you, if you match the two up, where the crater is. It's huge. It's at least 200 kilometers in diameter, probably a little more than that, which would mean that the asteroid that hit was probably 10 or perhaps as much as 20 kilometers across. But even if you look carefully on aerial photos, there's no real evidence here of a crater. So how did they figure out there was a crater? It turns out they did something that probably many of you have done as a high school physics experiment. Most people measure g, little g, the acceleration due to gravity. It turns out if you do that really precisely, it'll be different if the area under the surface has a different density because it has been impacted. And that's exactly what they did. This is actually the crater here. It's a highly detailed gravity map of that region. So Alan Hildebrand, a New Brunswicker, found the proof of the crater, found the crater proof, at least, of the extinction impact. So, all right, how often do we have to worry about one of these, and what are their effects? Let's look at that question. Back in June of 1908, in Siberia, in the Tunguska region, there was an object not very big, about the size of a football field or a little bit larger, and it didn't even make it to Earth. It exploded at least 8 kilometers up. But nevertheless, that explosion was enough that it flattened over 2,000 square kilometers of forest, literally millions of trees. This is a graph that summarizes the main information about let's start with the top axis. So the top axis gives us in meters the size of the object. The right-hand axis gives us how frequently, if coupled to the line, that we would get that. Those are both in logarithmic scales, so you have to interpret them that way. And let's look here at the graph. So for example, Tunguska, this suggests was, well, somewhere between 20 and 90 meters. And how often it would occur, well, not quite as often as once a century, but much more often than once every 1,000 years. What about Chicxulub? That was the crater that Alan Hildebrand found in the Yucatan. It would occur about once every 100 million years. And it's, according to this estimate, about 9 kilometers across, 9,000 meters. The bottom axis here gives you the energy in megatons of TNT, and that means exactly what you think it means. Imagine a convoy of trucks lined up and filled with TNT explosives. If you had 1 million tons, that's a megaton. So let's just look at Chicxulub. This is 10 to the 8th, so it's 100 million, not tons, but megatons of TNT would be the equivalent of that. There's one other feature before we leave this graph. This dotted line here represents the difference. Objects that are smaller than that, so in this it's about 2 kilometers, we think could be devastating to a local area. Like if something like Tunguska happened over Toronto, it would be catastrophic. But the effects would not be felt worldwide, and there would not be extinction of species. If you are on the right-hand side, that is, if you're bigger than 2 kilometers, we feel that there are global atmospheric effects which would lead to extinctions. Well, what can we do about this? The very first thing we have to do is find potentially dangerous asteroids. And we've come a huge way in the last couple of decades on that. The graph in the top left here shows you the number of not asteroids, the total number of asteroids would be way higher than this, but the number of potentially hazardous near-Earth asteroids discovered per year. And more than 400, almost 500, are found every year. Luckily, most of these, but not all, are well below that threshold of 1 or 2 kilometers across, as the graph on the right shows. This is another way you could look at it. It's somewhat dated now, but it's a snapshot in time. On this graph, every tiny green dot is an asteroid. You can see that most of them are between Mars and Jupiter. This is the orbit of Earth. The red dots represent the near-Earth asteroids, objects that do at some point in their orbit, not necessarily at this instant, get close enough that they pose a hazard to us. Well, it turns out that some of the asteroids that are dangerous to us are very difficult to detect from Earth. And there's a simple reason for that. If you have an asteroid that gets to Earth's orbit, but spends most of its time closer than the sun, from the surface of the Earth, it's just lost in the glare of sunlight most of the time. The best way to search for these asteroids is from space, and the very first satellite with a mission to look for asteroids was launched by Canada in February of this year. You might be interested because you might remember this is the person in charge of that. Yes, indeed, the same Alan Hildebrand. The next thing that we have to do is think about, if there is one on a collision course, what can we do about it? And the good news is, it turns out the push you need to give it is not very much if you can do it long enough ahead. And long enough means years ahead. Nevertheless, you need to come up with some scheme to give it a push. And most of them work on the same principle. If you took a balloon and if you let air out this way, we all know the rest of the balloon goes in the opposite direction. So by exploding something just off its surface, or perhaps just vaporizing it, that's what we try to do. But the effect of those things will depend on what the structure of the asteroid is, and the best way to know that is by studying pieces of asteroids that just fall to us, called meteorites. And one of the most important meteorites fell in Canada about a decade and a bit ago now. All right, there's a competition where you submit technical papers called Move an Asteroid. I doubt that you'll have time to get your entry in. It's day after tomorrow is the deadline for this year, but you have a year to work on for next year's competition. I I just wanted to end with, this graphic and then a concluding statement. When I was putting this together, I thought of a night back in November of 1998 when I was on the Gobi Desert in Mongolia with a team that included Alan Hildebrand. And we were there to study an impending meteor storm and provide information to satellite operators. But the image that is forever fresh in my mind, as much as if it was yesterday, had nothing to do directly with meteors. Alan and I were setting up equipment, and then we looked and saw in a little distance from us one of our gears or yurts completely on fire, and two of the people in our team, the silhouettes of them on fire. I've never seen anything so terrifying in my life. And in that moment, I sort of froze. But Alan, in a calm, efficient way, took control, and no one was seriously hurt. So we shouldn't be surprised that he has similarly responded here. So the final message I want to leave you with, and that's why I tied Alan into this so much, is you shouldn't get the idea that important science is done by someone else. Progress in science, just like other fields, are done by people like us, people like you. And if you know of youth that have interest in asteroids and dinosaurs and space and solar sails and what youth don't, please encourage them, because you never know, maybe the next Alan Hildebrand will come from Moncton instead of Fredericton. Thank you very much.